I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast.
Hey Ben.
Hey Matt.
So, last time we were talking about performance, and amazingly, you and I have remembered just about enough of what we were talking about before to be able to continue on that subject.
Yep.
So the story so far, as we were recapping during the intro, we have a relatively trivial piece of code, and we were interested in making it go as fast as possible, mostly by looking at the things outside of the code itself that could be taking time, I/O and shipping things magically through kernel space or avoiding kernel space, all that good stuff. So then you said, well, what happens if it wasn't a trivial piece of code? What if it was like a lot of work? How do you make that go fast? And I think that's where we were going to continue. So, I mean, how do you want to start this?
Well, so yeah, like the previous example, it was dominated by I/O, right? Like,
or a very simple map lookup and just RAM, and we talked about L1, L2, L3, and that kind of stuff.
Yeah, not quite adding two numbers together. You do maybe have to go out to RAM and pull some data down, but I think I Redis cache was sort of like the
mental model we had exactly. Yeah.
And maybe alternating with robot servo control, but that's I think we went off on a tangent.
That's right. We both, unsurprisingly.
Yeah. So now imagine the program that I wish to make go fast, instead of being dominated by I/O, let's say is dominated by the program itself. And I think this is could be interesting in two dimensions. One is you might have something where what you're actually looking for is throughput, right? You're just trying to process a lot of data, or maybe you're not trying to process that much data, but the computation on that data is very expensive. And so you're trying to do that as quickly as you possibly can. And then there's also the dimension of just latency, where it's like, okay, I/O is maybe not the dominant factor here, but the round trip time of this still matters. And so you have trade-offs that you now need to make. Whereas before we were just kind of optimizing for, let's stay in the L1 cache and let's make sure that we never miss it. It's like, we can't. This problem is too complicated for that. So now we maybe have some interesting trade-offs between I/O and performance inside the CPU.
To sort of concretize, something like that a word?
That's a word now.
It is a word now. Something like a video game is a great example of, there's a ton of stuff going on in every frame, but you want it so that when you hit the fire button, you aren't waiting 120 milliseconds before you actually finally see the fire, the shot go off. And, there's a number of things that are sort of kernel bypassy in the way, but most of it is just down to computation. And can you get something done in, say, a 60th of a second or a 100th of a second in modern things. Right. And then for a throughput-based thing, we're talking maybe credit card processing. I don't know. That's still IOE feeling. I don't know. I'm trying to think of an example that might be that we could talk about. That's,
there's all kinds of problems with like text manipulation. Like you've got lots and lots of text. You're trying to summarize it, extract some, signal from it, run some NLP process on it. That's one.
Right. And you've got tons of data to go through and you just want to get through it quickly. But, any one piece of text is not particularly important.
Right.
Yeah, I mean, that works. Yeah. Well, so I think probably something we didn't even talk about last time, or I don't remember talking about last time, is the single most important thing about any kind of performance, which is measuring it and making sure you know what you're doing
yes,
before you make any changes. Because unlike almost any other aspect of software engineering, there are so many hidden variables and so many weird things going on inside computers or exogenous or in your own code, which is more complicated than perhaps you remember it is, or there are surprising aspects of it, that the only way is to establish some kind of base truth, like I have a representative amount of work and I have a harness that can run it and I can get reproducible results that are hopefully intersubjective, so I can share it with my team and they can run it and they can also see that, or that kind of thing first, before you even start making the first change or even trying to understand the problem. You just need to have a baseline.
Right. Right.
So measure, is the key there. And then profiling is the next sort of aspect of it. Like, how do you know where you're spending time in your program? And that can be a surprising journey as you discover that actually it's not the computation, it's not the big O of n squared thing that you've got. It's the fact that, unbeknownst to you, the particular function you're calling has to do a locale lookup every single time to
Right.
parse a string, and you didn't realize that it was just checking. I wonder if the user has switched into German locale and they're expecting us to use.
It treats this identifier as a domain name and does a DNS lookup every time you call this function, right? Yeah,
Right,
exactly.
yeah, exactly. Understanding the complex code that you have written and that you're interacting with,
Yeah.
and the surprising effects it has are key. So I realized we didn't really touch on that last time, but that would be like the first and most important thing is measure everything, and then you kind of hit the sort of list of, do I need to do this? Can I do this before? And then can I avoid it? Those kinds of things. I can't even remember who was it? Somebody we spoke to once had a list of like these sort of like rules of optimization. The sort of zeroth rule is, do I even need to do this at all?
It's always
But
that's
anyway,
a
I'm
good
getting
rule
ahead of
for
myself.
anything, honestly.
Yeah, that's true. That's true.
Okay, so let me to kind of kick this conversation off. Let me throw a scenario at you because everything you're saying here makes a ton of sense, right? And so, like, okay, yeah, measure at least twice, cut once, right? Like, I'm going to measure this thing. I'm going to make sure that it is slow. I'm going to maybe have a profile that tells me that it is the slow part in the context of the system. It's not that it has some slowness to it that I don't like. It's like, no, the reason that the bullet isn't traveling out of the gun fast enough is because this line of code or this method or this thing is slow. So let's say that I'm like, all right, well, obviously what I want to do here is I want to measure it and then I want to change it and then I want to measure it again and I want to make sure it got better, right? What do I do when I set up my little thing to measure it and I run it and I get one result and then I run it again after having made no changes and I get a totally different result?
I mean, despair. but be aware that that's very common, right? It's benchmarking anything is incredibly difficult, and with all the variables that we've talked about, the noise on your machine is perhaps a source of that. Making sure that there isn't an exogenous input that actually you're depending on, like you say, a DNS lookup that sometimes is in the cache, sometimes isn't in the cache. Those kinds of things, and then if you're on a shared machine, obviously, I guess it depends, right? There are some aspects of performance are so large. Like if you're measuring the throughput of a system and you're running it for like 20 minutes, and then you're getting results out of that, then usually the noise levels are low enough that it doesn't matter as much. But if you're doing something that's like the collision detection for a video game, and you're like, okay, I have I've got a test essentially, just like I would write a test to say, do these two things intersect? Except that it's a little benchmark, and I'm going to run are these intersecting over and over again? And each time it takes, I don't know, 200 mics, something like that. And then I run it once and it says 200 mics, and I change nothing. I run it again and it says 10 mics. I'm like, what? Hang on, this is bonkers. Now you're in the sort of like the noise of the machine area, and you are looking at things like the warmth of the cache, whether or not other processes are running at the same time as you, whether you're being kicked off the CPU, whether or not you've got Slack open in the background, and someone's just posted an animating GIF, and now 200% of your CPU is actually animating a stupid cat.
Yeah.
Those are the things that you immediately think about. If you can rule out some sort of internal differences like the DNS related thing, or like maybe there's even a cache file on the disk and whatever. And there are frameworks for running benchmarks that try to do their best to isolate your process. They will warn you if you haven't like turned off other certain aspects of your CPU. So for example, the CPU can throttle its speed up and down for power saving reasons, and so that might be a reason. Like the first time you ran it, it ran slowly and then it ran fast because actually the CPU woke up and was now faster. The actual gigahertz clock frequency. So there's a ton of sources of noise at that level, and realistically, when I've done this kind of stuff for the more micro optimizy stuff, it's best to try and have a dedicated resource somewhere. So we've had like CI machines before now that have been things that we can reserve and or run continuous performance monitoring on critical pieces of code, and then just keep a graph of it. But it is noisy. There are tools you can run. So I have a friend who swears by using Valgrind, which many people know as being like a memory checker for compiled languages, but there are other modes that it has, and one of the modes that it has is like to count the number of instructions executed. It kind of virtualizes the whole thing, and it runs as a sort of an emulator of the very CPU you're running it on, which is kind of how Valgrind itself works. But it gives you a deterministic how many instructions did this code path take, which is interesting.
Yeah, so you're not measuring it by time anymore, right?
You're not measuring it by time. And of course, that's not necessarily a perfect proxy, because ultimately you want how long did it take is you're trying to optimize. But if you, for example, want to put something in CI where you could say, literally write a test that says, if this function takes more than 20 million CPU instructions, then we've probably done something dumb somewhere. Like either we've forgotten a command line switch, or someone added something huge to a function. So it's a very gross check, but it is one that you could consider doing. And similarly, within that, there's a cache grind, which tries to estimate what a cache might look like. And in fact, actually, only today somebody posted. I'm going to just go over to my other screen here. Sorry for the sound changing. Someone's just posted a tool called Cache Explorer, which tries to tries to run a little bit of code and give you a visualization of what cache things have happened by simulating a cache. But again, we don't really know 100% what caches are doing and AMD's caches are doing, but we can make some guesses. But those are the kinds of things that might be unstable between runs.
Interesting. So in that world, you are, and I think there's a few different things here. So you're talking about like you could have a continuously running performance test, continuously running in the sense of it runs on every change, runs on every build.
Or once a night, 2 a.m, or something like that, where you can say hey, no one this is working right now. We've got all these resources that are dedicated, and there's no other noise coming from it.
Yeah. And, obviously you can try running those sorts of tests on dedicated hardware. You can try running the tests by not measuring time at all and just by counting instructions, which should be relatively stable, even if the cat GIF is running. And is your usual MO to then reuse those types of tests for performance optimization? Are you running the same tool that you would run in your CI process when you're like, oh, I need to optimize this method? Or are you building things that are more bespoke?
It depends, honestly. There have been times when I've used the same tooling. Those micro benchmarks are a great source of things to look at, but it's really, really easy if you're not very careful. Again, it depends on which domain you're in and we're talking again from the kind of industries that we've been in, where we have a very usually homogeneous deployment environment, where it's like, well, we have many computers that all look the same, so they have this CPU in them, and we have the luxury of targeting that CPU, or caring about this particular amount of RAM and number of CPUs and all that good stuff.
Right.
But typically, developer workstations are not necessarily the same as the servers you're deploying to, and it can be easy to fool yourself by running micro benchmarks on your local developer hardware, and then be very, very sad when it doesn't pan out when you run it in production. So you really do have to be careful about drawing too many conclusions from local stuff at the sort of scale that we're talking about, with the hundreds of microseconds level. So it is antagonistic to doing like quick turnaround and sort of like TDD style. Hey, just make it go faster. You've really got to be able to run on representative data, which is hard, because it's really, really easy to write a micro benchmark which is representative on its face, but actually is a little bit too best case scenario. For example, CPUs have caches, we've just talked about. CPUs have branch predictors. And so if you have a very branchy bit of code that you're running 100 million times in a tight loop with the same input data to sort of get you how fast this is going to be, A, you're hitting the same cache lines over and over again. B, the branch predictor has learned 100% of all of the branches in your benchmark and the benchmarking code around it. And so it is a perfect representation of the best case. Now, that's an important thing to understand. Like the min, this is something I see people do all sorts of distributions of these profiles, and like the min is an important point. It says like if everything lines up perfectly, then this is the theoretical best case that you can get. So the min gives you a piece of information, right? Then there's sort of like people talk about the mean, and I think that's a terrible representation of anything because like there's so many tails in there usually,
right?
So, but having an idea about what the distribution of your function looks like is important, and usually it's horrible log normal thing that it's not very amenable to understanding. But like looking at it and kind of getting a sense of like, are most of them less than 100 bytes, or is it just the average? I don't even know what. I'm not a statistician, but I do tend to look at plots and CDFs and things of that of what's coming out of the function under test. But yeah, winding back round to the cache and the branch predictor, if you don't have representative data, then yeah, you're when you then deploy to production and you discover that every time you call your function, it's the worst case because you haven't recently called it. The branch predictor has forgotten about it. The cache is not warm. Then you're hitting the worst case of everything. And then that doesn't dovetail. You're like, well, I made this improvement, but you don't see it. So it's almost impossible to do a good micro benchmarks. They can only be sort of representative. They can help you along the way, but you always have to run on real hardware, and you always have to run on like a real workload and measure something that you actually care about. For us in our world, it's usually like the end-to-end latency of a system that we care about. So you maybe say that going back to our Redis example, let's say it was a bit more, there was some bit more meat inside what it was actually doing, and you're like, well, I've optimized the hell out of this part, the bit that does a tree lookup for the cache key, and then there's some complicated stuff that goes on, and then we return it, and there's this, all this networking code that we've talked about. Well, you could probably sit and write a really good hash map implementation and all the benchmarks that go with it and think that you've done a great job, and then really you still have to see it in context of in the actual Redis server. Has it made a difference, or is it actually no? Well, this is great because it uses tons more RAM than before, and in my micro benchmark that just works a treat because I've got all the cache to myself. But when I have to share the cache with the networking code that runs around it, then suddenly it's not good anymore. I realize that's an incredibly long and rambly answer to your point, but
no, that's really good. And I can go back and forth and argue one versus the other about whether it's more important to have systems that are sort of, we talk about systems that are designed to be tested, systems that are designed to be observable. You could maybe argue one dimension of observability is performance, I guess. And so you could say, is this system designed to be profiled, right? Like, can you measure its performance under real world conditions with real world data? And the trick, of course, there is that, the more you care about performance, the more you care about not slowing down your performance by measuring your performance. And so having something that's running in the most real world environment, which is to say the actual production environment that is measuring performance, you might be questioning, am I making my system slower by measuring how slow it is? So what are some tricks that you've used in the past to sort of break this? I don't know that it's an iron triangle, but
that's interesting. There. Yeah, because we haven't really talked about that. We've been talking about sort of end-to-end measurements, be it because I'm running a micro benchmark and calling a function, and then literally the micro benchmarking in system is doing the like start the clock, call your function 100,000 times, stop the clock. That's how long it takes. That's Or in the case of our Redis thing, it's like, well, I have. I start the clock, I send a request to Redis, I get the request back, I stop the clock. That's how long a request takes. That's pretty obvious. But yeah, if you need anything more fine-grained than that, then usually some kind of instrumentation is what you want to put into your software. But to your point, somewhere along the line, that instrumentation itself takes time. And so you kind of got a Heisenberg effect of like, hey, I know exactly how long my program takes, and it's really, really long because it's measuring time all the, to a first automation that is all it's doing is getting the current time at any point in the program. And so there are lots of tricks you can do. I mean, there are definitely relatively low overhead timers that you can use. If you're in the weeds of microseconds, then it's useful in a C++ context to write yourself a little RAII style class, which is something which starts a clock in its constructor and stops the clock in its destructor, and then it squirrels away the number somewhere so that you know how long something took. And maybe you can accumulate over time all of the calls that fall into this scope. And those timers can be measured using the CPU's own timestamp clock, timestamp,
Mm-hmm.
which is a relatively low overhead measured in CPU cycles number that you can then later on turn back into a clock number. I mean, it's also nowadays actually the Linux kernel, if we're talking about Linux, is pretty fast at getting at the actual real time. But the TSC is a pretty decent, fast way of getting time. So that lets you accumulate blocks, and then you can at least sort of look for hotspots in that way. But then there are many tools that you can get that will give you more information, or you can write your own tools that sort of hierarchically arrange these, so you can end up with like flame graphs, which are these time divided, it's almost like stalagmites or stalactite looking things. They're, flames, I suppose that's what they look like, right? Certainly if you use the red colors. And so
Mm-hmm.
you see hierarchically where time is being spent. And that's a useful thing to have. So you can say, hey, I spend all my time doing this thing, but really in this function, it's because these three functions it calls are the things that take time. And you
Mm-hmm.
get that kind of view out of it. But there is a little bit of overhead there because you're measuring on the entrance and exit from those functions. And maybe you're having to write that down somewhere in like a log file or in shared memory or something like that. So those are all valid ways of measuring, but they have different amounts of overhead.
Mm-hmm.
I was going to say there's one other sort of trick, which is that modern CPUs have some amount of accounting that you can do within the CPU itself. And there are sort of two ways of viewing that. So a traditional profiler, which is, and by traditional, I mean like every profile I'd used until fairly, till sometime at a previous company, every profiler uses a trick where you set a timer, like in a CPU timer, and then after every 1,000 times a second, you just say, where the hell is the CPU right now? What program
Mm-hmm.
counter do I have? And then you do a little bit of work to find out what the stack is, and then that gives you a sample that says, hey, you spent this much time in here. And then you can sort of infer, if you can run your task long enough, then you get this great answer of like, well, you spend 30% of your time in malloc and 30% time in free. And
Mm-hmm.
you're like, well, maybe I need to think about my memory strategy. That's a great thing. And that's fantastic for throughput based things where you have a continuous workload that you care about it all the time. You just want the whole thing to be faster. So you can put that on. It's relatively low overhead. 1,000 times a second sounds amazing, and like really, really often. But to a computer, that's like eternities between sample points. And so if you can run it long enough, you get great results. If you're worried about latency, though, that's not much use. You typically find that you're spending 99.99% of your time in the wait for something to do
Right.
routine, and
Right.
then the samples never actually land in the code that you care about. So
Mm-hmm.
in the Redis case, for example, you would find that you've got to optimize your ePOL routine. You're like, no, I haven't. ePOL is just waiting
Right.
for a packet to arrive. I
Yeah.
only care
Yeah.
about it
Yeah.
when the packet comes in. And it's like, well, that thousand times a second timer never went off while you were actually doing anything useful.
Mm-hmm. Yeah.
And that's where like the instrumentation I was just talking about come into, because there you get to put the instrumentation where you care about it. But modern CPUs have the ability to do like essentially record. Oh, that's great. So we've got a car alarm going off somewhere in the background. I don't know if you can hear it, or I can, and I've got my noise cancelling headphones on. All right, well, sorry, editor Matt, you've now got something to worry about. But yeah, so the modern CPUs, Intel ones, can do like a trace of execution, and so they can essentially instrument themselves. And every time a call happens, or a return happens, or a conditional branch is either taken or not taken, some amount of tiny information is recorded into a buffer, and then you can ask it to write out that buffer, and then you can post process that and sort of infer what happened. And there are tooling. Linux has perf that can record this information, and then there's things like Magic Trace, which is like a set of user scripts over the top of it, and a nice website that lets you view it in like a timeline diagram. And that's an eye opener. Honestly, at that point, you've kind of got the whole world open to you, and every single nanosecond is accounted for you, and that's really quite something. So I forgot what you asked now. Again, you
No.
see, this
No.
is what
This is
you keep winding me up and watching me go.
No, this is great. I mean, you answered my question exactly. So let's say that you do all these things and you find the part of your code that you're now fairly convinced is the reason that it's slow, right? And at the risk of having you just recount the Compiler Explorer origin story, now what?
Well, so that's funny you should say that. Yeah, the Compiler Explorer origin story is almost somewhat orthogonal, actually. In some
Okay,
ways, that was a little bit.
it's
But
not. What instructions is this code generating?
well, it was, but that was more like arguing over whether the compiler was smart enough to make human
Mhm.
readable code as good as like the
Right,
awkward code that you used to write because compilers weren't smart enough, right? And that's
right,
so
right.
we're very much in the micro optimizations when we're talking about code generation,
Mhm.
and honestly, that's the fun bit for me. But very often, it's like
Yeah, it's
again the
just you're
things I
just
can't
doing
remember.
something dumb, right? Like it's not
Don't be
some.
stupid on purpose. Is like the
Yeah,
very first thing you should say. Is like
yeah.
am I looking this up in a map over and over and over again when I could just look it up once and remember it? Right now,
Mhm,
compilers are smart, but they're not necessarily smart enough to stop you from calling a whole function chain that is the look up something in the map. It may not, the compiler hasn't got perfect knowledge. It can't tell that like no one has changed that map since the last time you looked in it.
mhm.
And so this is the kind of thing you see. But again, these are relatively small wins sometimes. Um, Algorithms are important, obviously. If you're doing something dumb, if you're searching through a massive array of things when you could use an acceleration structure, be it a hash map or something else, then that's important. But then at this granularity that we're sort of talking about, sometimes it is actually faster to go through a big array than it is to like jump randomly around in memory that would be
Mm,
for
mhm.
like a hash map potentially. Uh, there's almost no case in which a linked list is the right answer.
I think that's yeah.
I have one special case of where I think a linked list is the right answer.
I really wanna hear this. When should one use a linked list?
So one should use a linked list when you need to keep an ordered list of things, not necessarily ordered as in like they let's say insertion ordered list
Mhm,
of things. So I've got a sequence of objects, and I can only ever add them to the back of that list, right?
mhm,
But I can arbitrarily remove them out from the middle of the list. And those, I'm given a unique identifier for that object by some external source that I have no control over,
mhm,
and it's associated forever with one of those objects, and I need to keep them in that sequence, right? But at any point, I could get a message saying, "Oh, number 79234 is gone,"
mhm.
and I need to be able to find it and remove it from that ordered sequence. But I need to keep the sequence. So you've kind of in the traditional sense, you might have a hash map to find that object, which is great. But if it's in the middle of a vector, like an array of memory, that would be
Yeah,
cool. You deleting it is not only really painful because you have to shuffle everyone beyond it down one, but you now have to go into the map of where everyone else is and I kind of update them to be in the new location that they're in.
mhm, mhm.
So
Yeah,
that's a pain.
yeah.
Um, Having a doubly linked list is disgusting, but given a pointer to just that object itself, all you have to do is like look at its next and prev and
Yeah,
wire them
and
up
connect them
together, and you're
together.
done.
Yeah,
And you're
yeah.
done. And so that's one of those examples where um, the 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 worst case is for a single operation. So like if I say I'm alluding to this. This is me thinking about an order book. So in our world of
Mhm.
finance,
I was
the
just
ex-
gonna say, this sounds like the, priority queue for an order. Yeah,
it's a
uh-huh.
price level for yeah, exactly. So
Yep.
you're told about these things, and that happens. So you could imagine you've got um, thousands and thousands of orders on a single level, and it's important to keep them in that sequence so you know their
Mhm,
relative priority. Whenever anyone trades, it's always the order at the front that trades away, which is kind
mhm.
of the worst case for if you did keep them in a vector,
Yeah.
right? But you could always store them backwards, and then that's a good case. right?
Yeah,
Maybe that works. That's
treat
sort
it a
of
little more
weird.
like a
And then you're
stack,
kind of like
basically,
the
in the
ones at
room.
the back. Yeah, exactly. Which is not, and there also there are things like decks, double-ended queues that have like this sort of capability of being like multiple slabs, which you can chain a linked list effectively of slabs. You could chain a new linked slab at the beginning or unchain it moreover. So those are all great and cool and everything. And it's very, much more cache efficient to have them laid out that way. But it does mean that the worst case is worse, right? Like whatever it is, be it the front order or the back order, depending on which one you've optimized for. If you have to remove that one, then suddenly you're shuffling however many thousand other orders around potentially. So that's bad. It's probably the case that the linked list based version is always worse, but it's consistently there isn't a bad case, right?
Right. You
And
get
so
the
that's an
same
interesting
amount of
trade-off.
worseness every time. Yeah.
It's an interesting choice. And, I've seen a number of book implementations in my time, and there's just different trade-offs. It's a really interesting data structure to try and optimize and ask the question, why would you do it this way? I've just started working in a new company, and I've seen another way that it can be done, which I can't talk about, but it's fascinating, and I'm really, really excited by. But that's how it is. So that's an interesting one. So anyway, the algorithm can be important. That's why I think when we got onto this. And then caching, not doing work that you don't have to do. So I think we've said like the questions you ask yourself are something like, do I actually need to do this at all for each thing? And oftentimes you discover, actually, why are we logging this out? Let's just take the log line out, right? Or put it behind a guard so it doesn't happen in production. It only turns on when we want that log or whatever. So it's an expensive piece of work. The classic example here is that you format a bunch of strings and then you pass them to debug log, which is not on in production, but you've already done all the work of formatting all the strings, and you're like, well, hang on a second.
Right.
I don't need to do these. Another thing is, do I need to do this now? So can I cache this ahead of time? Is it just something I could do at program startup? Can I make a reasonable guess as to the values that will happen in this particular thing?
Yeah.
In which case, maybe I take some time at the startup and I pre-populate a lookup table with all the possible values, and then I say, okay, well, it's just a lookup now at runtime. There are other tricks in that world where you can say, well, do I need a perfect answer to this now, or can I defer updating something until later? Or can I have another thread post me back occasionally saying, hey, this is the amount of whatever's that are available. Can you be conservative and get away without on your hot path doing the really complicated stuff and then push other stuff to other threads? I'm trying to think of the sort of obvious things here, and
So how often, I feel like there's this almost myth of, and I have to wonder if anyone has ever come up to you with questions like this, the myth of the expert programmer that has like the function that is taking all the time, and they're like, I'm going to rewrite this in assembly code and it will be super fast because I have written it in assembly code. Like,
so yeah,
does that actually happen? And when and why would that actually happen?
So yes, but it's something you have to do very advisedly. I'm trying to think about how I can say this without breaking any confidences, but I'm aware of certain critical core loops in certain circumstances where compilers just aren't good at intuiting which variables are the important variables, and no amount of tagging them can convince them otherwise. And so they forever spill onto or off of the stack for those things. And in one specific case, rewriting the core loop of something, and by a core loop, I mean it's a chunky piece of code, pages of assembly at least. Writing that in assembly was a definite win. In terms of not spending half the time pushing and popping or reading and writing to memory, which has its own issues to do with aliasing and stuff. We've grazed at before in some of the conversations we've had about the clever tricks that register renaming that can happen if you use registers, but as soon as you put it into memory, a whole new system has to come in and it's a lot more complicated and slow. Anyway, so yes. And there are also some other examples where if there are specific instructions and sequences of instructions that do specific things that you need to do, then sometimes cracking out the assembly is worth it. Although less often now that most of the instructions are available as intrinsics that you can call, or library functions that have the same meaning behind the scenes and have basically been invented to wrap the underlying hardware's capabilities. And then you can phrase things in maybe a slightly tortured way where, you have to call underscore underscore some weird thing to get some function and assign it to some weird type, and then write your instructions, not instructions, write your code out longhand where it's like underscore underscore add of bracket underscore underscore sub of x comma y close brackets comma z, that stuff, rather than the more, but you can get it to generate the right code. So both, but at that point you're really just using the C compiler to write the assembly code that you would like it to write, and that's still better than writing the assembly. So to answer your question, yes, but it really, really has to be worth it, because more than anything else, you're trading off the ability to change and understand your code down the line. It's so fragile. It is so very, very fragile once you've written it in assembly, and you have to be so sure it's right. So testing's important, and keeping a C version of it around that you occasionally race with a new compiler against your other input optimization, version.
I was going to say, I feel like one of the things you give up by doing this is the ability to just upgrade your compiler, and then all of a sudden it's faster, right?
Right. Exactly. So that's that. I think the times that I've known that has worked, and this is not anything I've done for what it's worth. I haven't written a substantial amount of assembly code since the 90s. But where it has been known to work is where folks have taken the time to carefully write some assembly for something that's really, really important, and then keep a C version of it next to it, and then have continual races against the C code versus the assembly code on upgrades, and also correctness checks against the two. This is
right.
We run inputs on the C code, and then we compare it against the output from the assembly code, that kind of stuff. But yeah, it's tough, man. And I mean, another example of where you have to write assembly is if you're interacting with kernel magical stuff, like that. But which for some of the more esoteric profiling things, you might have to do an instruction here and there to get. But yeah, usually no. Usually, the flex, in my experience, the flexibility you get of leaving it in C or C++ and having the ability to quickly manipulate, move things around, change around, play with compiler flags, and let essentially 40 years of other people's experiences that have been poured into the heuristics of a compiler at my code, they're usually better than most things I can come up with. And the times that I found I can substantially beat the compiler with assembly have been times where I have been unable to explain correctly to the compiler the unwritten constraints that I'm aware of that it is not, or vice versa. It is being more conservative. It doesn't know that writing through pointer X and then reading through pointer Y, those two things will never be the same address, but I do. And so if I write the code that way, of course I won't. I'll read one into a register and keep it in a register the whole time. Whereas the compiler's like, well, every time you write to Y, I have to reread X again, because for all I know, Y points at X, that kind of thing.
Yeah.
Gosh, that's a lot of things to talk about abstractly 40 minutes into a podcast.
So I got one. I don't know if this is, I'm just going to ask this question. So
go ahead.
Talking about perf and using perf, a tool that I have also used for just answering generally the question of what is my code doing for lots of reasons, performance optimization being one, is strace. What system calls am I making? What are the arguments to those system calls? When are you using one versus the other? When are you using perf? When are you using strace? What problems are you trying to solve when you use those tools?
Yeah, that's a really good point, actually. strace is like the go-to, isn't it? For if something's taking a long time, that I don't have the source code to, I'm going to strace that thing and see what the hell it's doing.
Yeah,
it's
going back to it's doing the DNS lookup, or it's doing the weird file system call. Right. Yeah.
Exactly. And so if we're talking about very high performance things like we have been, then if you're doing it right, strace will show you nothing, because you shouldn't be interacting with the operating system. If you're the instant you're calling fwrite to write to a file, you've already lost, right?
Mm-hmm.
That's not a high performance piece of code, right? And that's perfectly valid. I mean, obviously there are loads of bits of high throughput code that are going to call F right, and then you do want to look at S trace. So maybe that's your answer. If you're looking for latency, you won't see anything, but for throughput, it might be a really good indicator of like, am I spending a lot of time waiting for the file write to finish happening? So strace is very valuable for that kind of thing. There are other tools as well. So there's various eBPF based stuff that I haven't had much personal experience with, but so my knowledge goes back to System Tap, which is like another similar thing where you can hook into more parts than just system calls. You can say like, hey, call this function effectively in like a funny little scripting language every time there's a page fault, and then I can aggregate page faults, and I can see what the heck's happening there and give me the stack, and then I can work out, hey, wait a second, we've just allocated a massive slab of memory and then we're getting all these page faults, what's going on? And you realize, oh, of course, although I think I've allocated a big slab of memory, the operating system has just given me a big gaping empty hole of virtual address space. And then every time I read or write to it, it decides to now fault in the 4K page. And that takes a bit of time. I'm like, no, I don't want to do this. This is a low latency thing. Like, at the program startup, I'd like you to do all of that, please. And then I don't have to pay for it later on. Those kinds of things, and those kinds of stuff you can find from like a System Tap or dtrace in other operating systems, or again, there's something eBPF. So yeah, there are other tools available for sure, and I know that things like System Tap and eBPF based things can also patch function calls both in the kernel and I think in your user code as well. You can put trace points, and so you can kind of add some dynamic things where you can say every time this function is called, I want to know about it. I mean, like, funny true story, like, it's not the worst profiler in the world for throughput based things to just run it in GDB and hit Control C and say backtrace, where are you now? Okay, continue.
That's you're sampling. Control you're C. Just acting as a sampler.
Exactly.
Right?
But it's
sometimes it works.
Exactly. And another while we're just thinking about these things, another performance investigation technique is to just single step through your code. And if you get bored of stepping through stuff, then your CPU is taking too long.
Sympathetic profiling.
That's
right.
How
do I feel when this code runs? Do I feel fast?
Does it feel good? I mean, but no, I mean, joking aside, like, especially with the layers and layers of indirection that things like C++ can give you, and if it hasn't inlined everything and the compiler hasn't had heuristically determined that it's valuable to keep inlining until it nets out and says, well, actually this is just return 2, then sometimes you'll find yourself stepping into functions that step into functions that step into functions. You're like, what, where, how far down is this going? And then eventually you get to the return 2 and you're like, okay, I need to do something about this, right? This is not right, and again, people, I say this and people are like, oh, but in order to debug it, surely you had to do a debug build, and debug builds have no, aren't fast. It's like, no, we have to separate the idea of optimization, the -01, 02, 03 of like a C++ build from leaving the debug symbols around. And knowing that you can still have a completely optimized binary that has at least somewhat useful debug information, so that although inlining has happened and code has been moved all over the shop, and so if you actually single step through it, you'll see your poor cursor inside your source code jumping all over the place, but it still gives you some idea about what happened and where time is being spent and what things are going on. But yeah, so for me, I will always have debug symbols around, because it's like, why wouldn't I? Now, obviously, if we were shipping to external customers, that maybe we wouldn't send.
Yeah, you're leaking that information, or maybe your binaries are just a little bigger that way. And if you're sensitive about the
and
space,
it does slow down some parts
why
of
would
the
you
build.
not?
It can slow down the build in the cases because it's a lot of debug stuff to go on. But there are clever linkers that can do tricks and things. And so. But yeah, that's why strace. No, what was the question again?
No, I love that point of like, if you're in latency sensitive code and strace gives you anything, well, there's your problem, right?
Yeah.
Like that's great.
Although, of course, with multiple threads, you have to be a bit careful, because other threads could be doing system calls, and that's fine.
Yeah,
we didn't really talk about threads as well. There are all sorts of horrible thread sharing related issues that can come from that. And the fact that waiting on a mutex or not waiting on a mutex is sometimes an operating system level thing, and sometimes is a futex, and sometimes it's sort of slightly outside of the kernel, so that things can be, so it's complicated, man. I think that's the short version. There's a lot. It's a deep topic.
Well, we've gone 45 minutes on this so far.
Yeah, I think there's a part 3, isn't there?
Maybe we do a part 3?
Maybe.
I don't know. I'm not going to commit to that yet, but that could possibly be a thing in the future.
We could certainly consider that. We'll see how this goes out. Yeah. Well, we better stop because I've got to edit this. And I'm lazy. I don't want to have to do more than 45 minutes. Have you any idea how awful it is listening to yourself gabble and realizing all the mistakes you made while editing? There's only so much I can do in the edit to make myself sound intelligent.
On repeat and trying to cut out this that I said, and it's just like the worst thing in the whole world.
Yeah, I'm sure our listeners have noticed that recently I've stopped cutting most of the things out because life's too short.
It's better this way. It's natural.
This is our listener is sat on the table next to us in a restaurant while we're having this kind of conversation anyway and just listening in. And that's fine by me.
It's the way to do it. All right, should we call it there?
Let's call it there, my friend. So I will see you next time.
Until next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at www.twoscomplement.org. Contact us on Mastodon. We are at twoscomplement@hachyderm.io. Our theme music is by Inverse Phase. Find out more at inversephase.com.